Greetings. Today I'm going to share the details about my machine learning project that I did with Skyfi Labs. My name is Manika Debnath. So far I have learned linear regression from Skyfi Labs and have developed a house price prediction model using the Boston housing data set which is present in the sklearn library. So first we need to import some libraries such as NumPy and Pandas. Matplotlib helps us to plot graphs and the sklearn library has functions like mean squared error, min-max scalar, and the function for splitting the data set. And we will also import HTML from IPython display libraries, for an animation of the training model of the data. First, we need to load the data. The data is called Boston and we can just load it with the command load_Boston. And if we print boston.descriptor, then we can obtain an output of the number of attributes present in the dataset, which are generally the features of the dataset from which we can predict the prices. Here, we have 13 attributes and a median value which is the 14th attribute. Next, we will store the features into a pandas data frame called features. And then we will print the data frame. We can see the result. There are 506 rows and 13 columns. We can also use commands like features and then call a column separately like age and we can see the values. Now, we will assign the target which is the prices that we need to predict. We will use the pandas data frame here to assign the target column here and we can print it. We can also use functions like min and max here to print minimum and maximum value for a feature like target here. Now, we just need to concatenate the features and the target into a data frame. We just need to use the concat function of the pandas library and the axis equals to 1 denotes the column-wise concatenation. By default, the value of the axis is set to 0, which means row-wise concatenation. We can also use describe data frame object to describe the count, mean, standard deviation, minimum, the percentile, and the maximum value for particular columns which are all displayed here. Now we just need to find the correlation between the target value and the features. Correlation is just a dependency rate of a feature and target, how the change in a feature affects the target. There are different types of correlation techniques available. Here, we are using the Pearson's correlation method. And we also will obtain the absolute values for every attribute in the list feature and then we will combine correlation values and features in a list. Then we will sort them and zip them again. Now we will use the matplotlib function to plot the graph against the attributes and see how they are dependent. Here we are taking the absolute values so we get a positive graph. But if we just remove the absolute function we can plot the graph in which we have negative values as well as positive values for the correlation between target and attributes. So, we can see that lstat is an attribute on which the target value depends inversely. And the rm is the attribute on which the target value depends directly. Then we need to normalize the data. We will use x equals to the lsat feature because it possesses the highest correlation with the target values among all other values. We will use the target column for y. Then, we can normalize the data using the min-max scalar object and create an instance and use the fit_transform function. We use the reshape function because the fit transform only allows vertical data, then we can utilize it to change it back. Then we need to split the data into testing and training set. We take 80% of the data as the training data and 20% data as the testing data. Now, we have to define some kind of cost function. Here, we are using the mean squared error function. We need to define 3 functions for it to run. We will define error to find the mean squared error. We will define the update function to update the m&c slope for the linear regression equation, y equals mx plus c. We will define the gradient descent function in which we can have several iterations in a loop and check for error every time. If the mean squared error is less than the threshold value, we can break out of the loop and append all the gathered error values in their list. And then return the final m and c values for the prediction. Here, we use the gradient descent function, keeping the learning rate at 0.001 and after running the gradient descent function for training the model. On the trained data we can plot the regression curve, which is the training data and prediction values. We can see that the slope of the curve is negative because the LSAT feature that we used for training the model has a negative impact on the target values. We can also see the errors with the iterations. We can see that the errors have gradually decreased over the iterations. And we can also visualize the training phase of the model by using HTML from IPython display libraries and the Func animation object. You can see in this video how the model trains itself. The regression curve changes accordingly while the m and c changed. And now we can get the predicted values using the y equals m asterisk x plus c, the equation of the linear regression. We can also test the mean squared error against the target values and the predicted values, which is 0.016 for LSAT feature. Then we can just add the target values and the predicted values in a data frame and show them. And we can also plot the scatter plot of the testing data and line for the predicted, and we can see the results. Also, we need to find the predicted data in target values. We have to break it up in a normalized form, so we need to revert the normalization by scaling it. We can use the inverse transform function for it, and then after scaling we can just put it back in a data frame to show target values, which is the y_test and its corresponding predicted values. We can also change the feature to RM, which has the second highest correlation with our data, and RM also affects the target values positively. And we can see the result that here the graph for the regression curve after training and the slope here is positive because RM is directly proportional to target values. Enum video. Here, we can see that model now has changed its direction and the slope is positive. The mean squared error here is approximately 2 times the mean square error for LSAT. We can also change the feature to something which affects the target value at a minimum rate. As Chaz is a dummy attribute, we will use dis. After the training of the data has been done using the gradient descent function, you can see the slope and the values are scattered around because the target values are affected less by the dis feature. Also, the mean squared error is 0.04, which is approximately 4 times the error found when using the LSAT feature. And these are the predicted values for the feature dis. So, Concluding, this is what I would like to state, that in linear regression we should always select the feature with the highest correlation with our data to fully minimize the cost function. Thanks for watching.